But in the same manner, we have different other examples also for simple harmonic motion. Let us consider the second example as a loaded spring. The example what we are having now is a loaded spring, and the vertical oscillations of the spring when it is loaded also are said to be simple harmonic by nature. So, when we consider a spring this way, which now is suspended from a fixed point like this, and a block of mass m is attached at its end, at one end of it. Now, naturally the total spring will be elongated a little. What I do in this case is, holding the mass, I just pull it down further a little and leave it. Then you find that it is oscillating in the vertical plane simple harmonically. One thing you can understand, this one when it is brought down this way, it has been brought down this way to this position and leave it, then naturally it goes to some height also after crossing the mean position of rest. That means, its position if I consider to be A earlier, it has been brought down to B, now it goes up to C and it oscillates in between B and C simple harmonically, crossing the mean position of rest A always. Once again one can conclude here that the acceleration is directly proportional to displacement taken in opposite direction. That means, certainly these vertical vibrations or vertical oscillations of the spiral, this one loaded spring, are considered to be simple harmonic by nature. So, what is the condition over here? If I take m as its mass, mg will now be the weight corresponding to that. When I say that it has been pulled down by a distance x like this, then naturally the elongation in the spring also will be x only. So, what we can understand in this particular case now, mg and the elongation both are supposed to be directly proportional to each other. Not only that, this elongation itself is the displacement of the total system, thereby you can say that this is opposite in direction to its acceleration. So, whether you pull it down or it is going up, whatever be the case, its acceleration always will be tending towards the mean position of rest, always it is directed towards the mean position of rest. Therefore, one can conclude that these vibrations, oscillations are also said to be simple harmonic by nature. So, when we consider, the same equation can be written as mg is equal to a constant k into x with a negative sign when I consider the magnitude only. Then we can rewrite the same equation this way as mg is equal to kx like. What is this k now to be called? It is to be called as spring constant. You can even rewrite the same this way also, it is also called as force constant. So, when we just write the value or equation for k, it will now be mg by x. This mg is nothing other than weight that is attached, divided by this x is now called as elongation produced in the loaded spring. That is the concept. Weight attached by elongation produced, and every one of you can understand straight away Newton per meter is its SI unit and mt per minus 2 the dimensional formula for this. Same dimensional formula you find even for surface tension. Therefore, same as that of surface tension. That is what we need to remember as far as this dimensional formula is concerned. Both are not same. only dimensions are equal, units are similar, that is the only point. And of course, k is equal to mg by x. When you take with a negative sign also, that negative sign gives you the direction part. So, magnitude wise you can take up k is equal to mg by x. Same equation let me take in a different way now. We in fact have seen just now that mg is equal to kx. What I do from this one is, I write the equation for x by g. What is its value equals to? M by k. X by g now becomes m by k. What is x and what is g, you understand? X is elongation and g is acceleration due to gravity. That elongation I can even call it as displacement, and this acceleration I can take it like this, acceleration due to gravity. So, when we consider displacement by acceleration is equal to x by g is equal to m by k. What is this m now? It is the mass attached at the end of the spring by this force constant, or you can even call it as spring constant, I have reminded you earlier. So, this is the full-fledged equation. We in fact know the time period of any body which is in simple harmonic motion, irrespective of the examples what we have taken up earlier. Any body, let it be in SHM, when it is in simple harmonic motion, what would be the time period of that particular body? T is equal to 2 pi under root displacement by acceleration. This is the basic equation what we all in fact know. So, whenever the time period of any body which is in simple harmonic motion we want to calculate, one need to calculate what is the displacement of that body and what is the corresponding acceleration the body is going to possess. If you know these two, you can substitute them here to finalize the equation for time period. Now, the question is, what is the time period of this oscillating spring? The vertical oscillations, already we have seen that these oscillations are simple harmonic. Therefore, what is the time period for the spring now? It is 2 pi under root displacement by acceleration. It is nothing other than x by g. But the same x by g is as well equivalent to m by k also. Therefore, 2 pi under root m by k I can write even the time period. So, there are two different formulae one can use as far as the time period of the vertical oscillations of a loaded spring. So, when you take this is the equation, one need to remember as far as the time period that is concerned. Now, what next we want? What would be the frequency of oscillations? N we can write it as 1 by time period. So, you can even rewrite the same as 1 by 2 pi under root g by x. The other version of the same 2 pi under root k by m we can write like that. This is the equation for its frequency as such. What next we want out of that one? What would be its angular frequency? Angular frequency, when I take it as omega, it is 2 pi n. Every one of us we know that formula well, and n already we have taken up in two different versions. Now, I can rewrite the same this way. Omega now becomes either root g by x, or you can rewrite the same as root over k by m. So, whichever that is useful In working out the problem corresponding to that, one can take that equation to finalize the result there. So, as far as a loaded spring oscillating in the vertical plane that is concerned, what is the time period we need to remember, and what is the frequency of oscillating loaded spring we have to take up, and one is the angular frequency, that is what we call it as omega, which is under root g by x or under root k by m as such. These are the major equations as far as a spring loaded with certain mass and made oscillated in the vertical plane that is concerned. As far as loaded spring is concerned, when we consider a loaded spring in general, already we have taken up T is equal to 2 pi under root x by g or 2 pi under root m by k. If you look at this equation carefully, k as far as a particular spring that is concerned, it remains a constant, and even the mass of the body attached at the end of the spring also is a constant there. So, whenever we consider this equation for time period or the equation corresponding to its frequency, both the values of m and k, since they remain constant for a particular spring attached with a certain weight at its end, the time period is definitely going to be constant. What do you mean by this concept of time period becoming constant? It in fact does not vary with the variation of g. What for you can better understand easily? K is equal to mg by x, the basic formula. When we consider g is a variable, mg varies. According to that only the spring is going to be elongated. That means always we find the value of mg by x that remains constant. Therefore, there is a wonderful question theoretically they can ask you. A spring clock and a pendulum clock, out of these two, which one you prefer to measure the correct time on the moon as well as on the earth? On the earth means okay, we can take both, there is nothing wrong in it. That also, when you are moving from one place to another, since the value of g is a variable there, the pendulum clock may give a different time over there. Whereas a spring clock, when we consider its value of k, that is spring constant, since it is a constant everywhere, and the value of time period remains constant always. Therefore, perfect time when we want, correct time when we want, always we prefer taking a spring clock there. So, that is one theoretical concept what they can ask you. Now, let us take few special cases of the springs. Say for example, if the mass of the spring, is m1, in most of the problems, whenever a body is attached to a spring this way, mass of the body only will be provided to us, not the mass of the spring. When he is not giving the mass, what is the meaning of it? When comparing to the mass of the bob or the body attached, the mass of the spring is negligibly small. But of course, there is no rule every time that mass is supposed to be neglected like that of any spring. If mass is considerable, if mass is supposed to be considered or taken into account, then how to write these equations? For that, I am just giving you a special case. If the mass of the spring is given as m1, then the time period has a different formula, that is 2 pi under root m plus m1 by 3 by the value of k. So, this particular approximation whatever we are taking up is no doubt an empirical one, but one need to remember when mass of that spring is specially mentioned in the problem, you have to consider this formula to calculate the corresponding time period. Similarly, frequency, if you want, you can reciprocate and write that one. It is not a big task for any of you. That is one area you have to concentrate specially on it. Come to the second area where we have to concentrate on. There is a spiral spring this way. Its spring constant is now given as k. Now, what they say is, if the spring is cut into n identical parts, that is one point we have to understand. Identical, not of different lengths. What happens when the lengths are different, we shall discuss a little later. So, first of all, you try to understand, if the spring is cut into n identical parts, then the force constant, of each part, would be n times k. That is the formula one need to remember here. Whenever a spring of constant k is cut into n identical parts, the force constant of each part will be n times the value of k, which was the earlier force constant. For example, when I consider made into 3 equal parts, then k of each part, you can directly write k each is now going to be 3k. Suppose 2 parts 2k, 5 parts 5k, and so on and so forth. So, whenever we are cutting the spring into any number of equal and identical parts, then each part will have a force constant equals to the number of parts into the original force constant k. For example, n parts means nk, 3 parts means 3k. That is one area we have to concentrate on. Let us consider one more case of this loaded spring. This case we are taking up this way. There is a spring like this of force constant k. It is now cut into 2 parts of lengths in the ratio L1 is to L2. You definitely can understand from this wording that their lengths are not equal. They are of different lengths now, L1 is to L2. Then what would be spring constants of both the parts if the original spring has force constant K. That is the point. Original spring has got a force constant K. Now it is cut into two parts in the ratio L1 and L2. L1 is to L2, the ratio given. What would be the spring constant of the first part? What would be the spring constant of the second part? These two we just have to calculate. For this one, a simple concept you need to remember is, whenever springs are cut into any number of parts, whether identical or different, the basic concept over here to remember is that L into K must be constant for each part. So, what is the basic law here? Length of the spring into its corresponding force constant must be constant. So, what I can write in this particular case is L into K of the original spring must be equal to L into K of the first part, and that is equal to L into K of the second part as well. Like the way we people used to write Boyle's law or any other equation, P1 V1 is equal to P2 V2 is equal to P3 V3, similar to that almost. L into K of the first part and L into K of the second part, L into K of the third and fourth, fifth, like that any number is equal to L into K of the original spring. Then what is the equation we can write? First of all, equate these two. What can we write now? L1 plus L2 is the total length of the original spring into K, that is its effective value of force constant, that is of the spring, original spring I am talking about, is equal to, what is the length of the first part? L1 into, I write this one as K1. What is K1 here? It is force constant of the first part of the spring. Then how to write this equation now? K1 now becomes L1 plus L2 into K by L1. That is the equation for the force constant of the first part of length L1. Now, you equate the first one and the third one, please. Then what is it you are going to get again? I can rewrite L1 plus L2 into K is equal to L2 K2 I can write. This now implies K2 is equal to L1 plus L2 into K by L2. This is the equation what one has to remember for the spring constant or force constant of the second part of it. So, first part has got K1, second part has got K2. This is the case you need to remember. Similarly, sometimes they may say like this, springs connected in series. Springs connected in series. That in the sense you can say there is one spring like this, one more spring like this, one more spring this way, all the three. At the end of the third one, we just have attached a body of mass m. This is having a force constant K1, this has got K2, this has got K3. One thing you should understand, what is meant by springs connected in series combination. How can you identify series combination? Very simple. Body will be directly in contact with only one spring out of the lot. There are three springs, but the body is directly in contact with K3 only. It has nothing to do with K2, nothing to do with K1 directly. Therefore, what is the formula we all in fact know? 1 by K effective is equal to 1 by K1 plus 1 by K2 plus 1 by K3 and so on. Like this is the formula by means of which you can estimate the value of effective K. Then what would be the time period? T is equal to 2 pi under root m by K effective. Similarly, n if you want, 1 by 2 pi under root K effective by the value of m. These are the equations by means of which you can calculate either the time period of oscillating system or the frequency corresponding to that. Similarly, the second concept over here, suppose connected in parallel. Connected in parallel means you can have one spring here, one more spring over here. To both of them, we are attaching a body of mass m. This has got constant K1, this has got constant K2. Then what would be the result? The same structure even can be given like this also. This is mass m, this is one spring of constant K2, this is another spring of constant K1. Remember, both are parallel combinations only. Then what would be the effective value? K effective now becomes K1 plus K2. Like that, any number you may be having, add them all, and you can write now the time period is equal to 2 pi under root m by K effective. Similarly, frequency is equal to 1 by 2 pi under root K effective by the value of m. Sometimes they may even ask you what is angular frequency. Omega also you can write the same this way, under root K effective by the mass m that is attached at the end of the system as such. So, this is a parallel combination and this one is series combination. One can easily remember these two. You just compare capacitors connected in series. If you recollect once again from electrostatics, capacitors when connected in series, 1 by effective capacity becomes 1 by C1 plus 1 by C2 plus 1 by C3 and so on. Similarly, when they are connected in parallel, C effective is equal to C1 plus C2 plus C3 and so on. So, both are exactly similar by nature. Therefore, if you can remember this pair, you can reproduce those formulae there or vice versa. That is a concept one has to understand as far as the springs connected in series and in parallel that is concerned. What is the energy stored in a spring? Whenever we are compressing a spring, surely there will be some energy that can be stored. What kind of energy that is stored? So, energy stored in a spring, when we directly take up, potential energy can be stored in a spring. What is the formula for this amount of potential energy that can be stored? That you can write it like this, half kx square, where the value of k is a force constant and x is going to be either the compression or you can call it the elongation depending on the case, and u is equal to half kx square is the basic formula for us to calculate the energy stored in the case of a compressed spring. Fine. But what are its applications? Directly they may not ask you to calculate the energy stored, then if at all they ask you like that, it is excellent. Straight away half kx square formula you can adopt and you can finalize the answer, it is not a big task. But what is the application they can ask you? One example I just give you here. There is a table like this. On the table, there is a spring which of course is kept horizontal this way, having a force constant K like this. And what he says is, there is a block like this of mass m, which is now moving towards this spring with a velocity v, or a constant speed we can say. It is now directly going straight on the same table towards the spring which is kept horizontal on it. Directly the block hits that one and compresses the spring. So, what we have to understand, if the block hits and compresses the spring by x, compresses the spring by x, then what is the conclusion we can have in terms of law of conservation of energy? That is important here. Conservation of energy we are going to apply. Whatever kinetic energy of the block we are finding, that now must be converted into potential energy in the spring. That is the conclusion. The kinetic energy of the block is converted into potential energy in the case of the spring. So, what is kinetic energy? It is half m v square. What is the potential energy stored in the spring? Half k x square. Half getting cancelled on both sides. M v square is equal to k x square. This is the relation one need to remember. If you carefully observe this equation, there are 4 variables. One is mass attached, one is speed of the block, one is spring constant or force constant K, and one is the compressed length of that spring, that is x. Out of them, any 3 if you know, automatically you can calculate what is the 4th value. For example, if I want to know the value of x, then I can write this one mv square by k under root. Similarly, if they ask you to calculate the speed at which it is striking the spring, then you can write the same equation this way, kx square by m under root. Like that, they may even ask you what is the value of force constant of that spring taken up there. You directly can write mv square by x square. Similarly, they may even ask you what would be the mass of that particular block which is striking that. Then you can write kx square by the value of v square like. These are the 4 different versions you can write from this equation. Individual versions you need not remember anytime. Remember this major equation, mv square is equal to kx square, or half mv square is equal to half kx square, you remember. That is the major equation where from whichever value you just want, you directly can calculate using the same equation as such. So, this is the version what they can ask you when the block is striking and compressing the spring. Same question the other way also they can ask you. It has been compressed, fine, but will it be like that forever? No, once again the spring elongates. When the spring is elongating this way, the spring throws this block away from it. Then what would be the velocity with which the block is thrown away by the spring, they may ask you. Then also the potential energy of the spring is again equals to kinetic energy of the block, and you again will be getting the same equation, mv square is equal to kx square as such. Therefrom, whichever value he is asking you in that particular problem, you can directly solve it. So, that is one area what we have to remember as far as energy stored in a spiral spring that is concerned.